I love your car. How did you afford this thing?
Are you that TikTok guy?
I am.
A graveyard of failed planets, remnants from the heyday of planetary construction. We often imagine the asteroid belt to be a dense, unnavigable mass of tumbling rock, but in reality it's something quite different. The total mass of all those rocks is estimated to be 3 times 10 to the power of 21 kilograms, which, although an enormous-sounding number, is just 4% of the mass of our Moon, with a third of that mass found just in the largest object series. The rest of this cosmic junkyard is made up of objects covering a vast range of different sizes. On one end of the scale, we think there are at least a couple of hundred asteroids larger than 100 kilometers in size. Then come a million or so stretching to at least 1 kilometer or more, and a countless spread of smaller objects number in the millions and billions, depending on how small you want to go. All of this sounds like it should make for a crowded environment full of collisions, the perfect location to form the basis of a computer game or disaster movie. But even with that many objects, the space they occupy is so unimaginably vast, spread out across 13 trillion cubic miles of space, making the average distance between any two large asteroids approximately 2 million miles, or 8 times the distance from the Earth to the Moon. These distances are so large that when we send spacecraft to the outer solar system, the chances of hitting anything are so small that the engineers don't need to make any course corrections to pass through. In fact, if you were standing on an asteroid, you'd be lucky to see another one, and if you did, it would appear as little more than a tiny point of light in the darkness. As it travelled through this vast emptiness in the early summer of 2011, the Dawn spacecraft slowly began to bring its first target into view. From a distance of over 1.2 million kilometers, Dawn took its first photograph of Vesta against the backdrop of 1,000 stars. Over the next 2 months, Dawn homed in on Vesta, chasing it across the vast reaches of space to arrive at this, the second largest rock in the belt. Entering its orbit on the 16th of July 2011, Dawn became the first spacecraft to enter within the gravitational hold of an object in the asteroid belt. And for the next 14 months, it would explore this extraordinary ancient object, providing a glimpse of our solar system in the very earliest days of its life. When 4 Vesta, to give it its full name, was first discovered by the German astronomer Heinrich Olbers in 1807, it was the 4th asteroid to be discovered after Ceres, Pallas, and Juno, hence the 4 in its formal designation. Olbers was convinced he had found the remains of a lost planet, destroyed in some long-ago collision. Even so, just like the other 3 objects, at first Vesta was given full planetary status, bringing the number of classified planets in the solar system at that time to 11. It wasn't until 1845, nearly 40 years later, that a flood of further discoveries began. In the 1850s, 15 planets became 8, a point where it was clear they couldn't be classified as planets. And so in the 1850s, 15 planets became 8, and the classification of these objects as a different class of minor planet, asteroids, had begun. 160 years later, as Dawn began its year-long residency in the vicinity of Vesta, it soon became apparent that Olbers' suggestion that this was a fragment of a long-lost planet was not so far off.
Check out this new tablet I just got.
Wow, that's sleek. Where'd you find it?
Unity Wireless. It's incredible. The triple camera and high resolution make every photo look professional.
And is it fast?
Vesta is a spheroid-shaped rock, 530 kilometers in diameter and pockmarked with impact craters. The most striking example of these is the crater Rhea Silvia, which at 500 kilometers wide and 20 kilometers deep is one of the largest impact craters in the solar system. At its center is a mountain that rises into the blackness 22 kilometers from the crater floor, making it the second tallest peak in the solar system after Mars's Olympus Mons. What's particularly extraordinary about this crater is that we've long suspected that a particular class of meteorite found on Earth, known as HED meteorites, actually come from material that was blown off the surface of Vesta when this impact occurred around 1 billion years or so ago. Using Dawn's instrumentation, we were able to directly measure the geology of rocks in Rhea Silvia, and when compared with the samples on Earth, we were able to conclude that they are of the same origin. In one of the most beautiful examples of geological analysis in the history of the subject, we now know that we can hold a piece of this faraway asteroid in our hands and directly analyze the secrets hidden within it. When taken all together, the HED meteorites and the findings from the Dawn spacecraft have enabled us to paint a detailed picture not just of Vesta today, but also of its history. Dawn has revealed to us that Vesta has a metal-rich core, just like all of the terrestrial planets, including Mercury, Mars, Venus, and Earth. And analysis of its surface geology has enabled us to date the formation of the asteroid to a couple of million years after the first solid objects began to take shape in the solar system. These are just two of the clues that point us to an extraordinary conclusion. Vesta is perhaps the last remaining example of a protoplanet, a half-formed world from the very earliest days of the solar system. Frozen in time, this is a stage that every world we know of passed through, including the Earth. Vesta was on the way to becoming a planet almost 4.5 billion years ago, but something happened to stop its progress. While other worlds went on to flourish, and other protoplanets disintegrated in the violent collisions of the early solar system, Vesta somehow seemed to survive, a fossil of planetary formation for us to not only look at, but through a quirk of fate, actually hold. But this was not the end of Dawn's dive into our deep history. Departing Vesta after 14 months of study, Dawn fired its ion drive, leaving the orbit and heading off for its second planetoid rendezvous, at the largest of all the asteroids, Ceres. Dawn arrived at the dwarf planet Ceres in early March 2015, and from the very first moments of its observations, it sent back some astonishing images. Very little was known about Ceres before our spaceship arrived, but it soon became clear that this was a rock with far more of a story to tell than we could ever have imagined. A story that would help reveal a new perspective on the deep history of our solar system and the enormous influence Jupiter has exerted over it. The Italian astronomer Giuseppe Piazzi discovered Ceres on the 1st of January 1801, and at first he reported his findings as the discovery of a new comet in the region of space between Mars and Jupiter. But it seems from the start that all of his instincts told him this was something else. In announcing his observations in a letter to two fellow astronomers, he noted that since its movement is so slow and rather uniform, it has occurred to me several times that it might be something better than a comet. Piazzi and his colleagues speculated that rather than a comet, they might have found something even more spectacular, a new planet. But after just 41 days of observation, Piazzi fell ill. The path of the newly discovered object strayed into the direct glare of the sun, and in a twist of high astronomical drama, the newly found planet Ceres was lost.
How much do you spend a week on groceries?
For two people, probably $200.
$200?
With just a tiny number of observations across a small piece of sky, calculating Ceres's orbit was deemed impossible using the mathematics of the time, and many contemporary great mathematical minds predicted it might never be found again. It would take the work of a young German mathematician, Friedrich Gauss, to solve the problem. Attracted to the difficulty and elegance of using mathematics to compute the orbit from just a few coordinates, Gauss pioneered a novel mathematical method that allowed him to calculate the path of Ceres using just 3 of Piazzi's original observations. On the very last day of 1801, 2 astronomers using Gauss's methods searched the region of the sky to which the calculations guided them, and to everyone's delight and relief, recovered Ceres from the darkness. Gauss became a mathematical superstar, and Ceres, firmly back in our sights, was stamped with the classification of a planet. For the next 50 years, Ceres and its companions, Vesta, Pallas, and Juno, remained listed as planets until, as we have seen, the discovery of a raft of other objects in this region of space gave rise to our identification of the asteroid belt, and for Ceres, it was downhill from there on, until in 2006 it was classified as a dwarf planet. For the next 160 years, little was known about this tiny planet orbiting the Sun at a distance of 413 million kilometers. We knew that it was the biggest object in the asteroid belt, and the only object amongst the millions of asteroids that was large enough to have been rounded by its own gravity. We could also make a good approximation of its size, at around 1,000 kilometers in diameter, and composition, rock and ice, what else? But when it came to surface features, even the powerful eye of the Hubble Space Telescope could make out only the vaguest of features, intriguingly strewn across its surface. It would take Dawn's arrival for us to truly understand the complexity of this world and its history. Even in the early approach phase of the mission, Dawn was able to capture a quality of imagery that at once gave a new perspective on the long-hidden surface. It was no surprise to find it heavily cratered, but while speeding towards Ceres, Dawn beamed back a series of mysterious images, revealing a number of bright spots on the surface of what we had thought would be a dull, dead and frozen world. Not what you would expect on a planet that was assumed to be entirely geologically inactive. The brightest of all of these highly reflective areas was imaged near a massive crater known as a crater. At 92 kilometers wide and 2 kilometers deep, it's one of the biggest on the surface of Ceres. Spot 5, as it became known, is in the center of the crater and became the focus of intense investigation as Dawn began its 3.5-year residency in orbit around Ceres. The crater is thought to have formed from a large-scale impact around 80 million years ago, and so the presence of what appeared to be geological active material on the surface was particularly surprising, and at first left the mission scientists perplexed. Not only that, but a haze was also seen to periodically appear above Spot 5, suggesting something was going on beneath the surface. After detailed analysis using Dawn's full range of imaging and spectroscopic capabilities, we now believe that Spot 5 is the result of a geological hotspot. The brightness created by the highest concentration of carbonate minerals ever found outside the Earth, in a dome structure right in the center of the crater. Why does this matter? Well, we know that this type of salt can only be formed in the presence of liquid water, and it's almost certain that an impacting asteroid could not have delivered such material to the surface of Ceres, so the upwelling in which it's found suggests that it comes from deep within this world. It now seems that Spot 5 is the remains of an ice volcano, one that is perhaps still partially active, and thus able to create the haze we have observed. The two brightly coloured patches inside it are thought to be the salty residue left by this ancient formation, deposits of sodium carbonate from an erupting ice volcano that may have first been triggered by the impact that created the crater. However, the dome-like shape upon which the deposits sit is almost certainly evidence of geological activity below the surface, suggesting that hydrothermal activity was involved in bringing the salts to the surface. And Spot 5 is far from isolated. We've now seen areas like the ones in Akator all over the surface of Ceres, and this begins to paint a tantalizing picture of Ceres' past, a past where heat from within the planet created a subsurface ocean, or at least localized pockets of water that surged upwards in the form of great ice volcanoes, bringing with them on the asteroid the carbonate salts that we see sparkling today. As Dawn delved deeper beneath the surface, the surprises kept coming thick and fast. Dawn was able to accurately measure the overall density of Ceres and found it to be 2.16 grams per cubic centimetre, which is less than you'd expect for a rocky body. Ceres is about 2/3 the density of our Moon, which suggests that as well as rock, the asteroid must also hold significant amounts of water ice. This had been suspected long before Dawn arrived, but with our eyes and ears now at work, as Dawn circled Ceres, it was able to take precise measurements and so uncover anomalies in its orbit that revealed something remarkable about this lump of rock and ice. By carefully mapping the shape and gravitational field, we found that the rock and ice weren't evenly distributed. It appears that Ceres' interior is nothing like that of other asteroids in the belt. Instead, it appears to have a rocky core surrounded by an ice-rich crust. This is not the jumbled structure of an asteroid. The differentiation into layers that was discovered by Dawn is something we only see in planets. It seems that around 4.5 billion years ago, Ceres had taken its first steps to becoming a fully fledged world, and then something went catastrophically wrong. So we now think that 4.57 billion years ago, a young rocky planet began to form in the region we call the asteroid belt. In its infancy, this protoplanet was a water world, warmed from within by the heat left over from the violence of its birth. Even in this frozen region of space, orbiting 413 million kilometers away from the weak young sun, a deep saltwater ocean encircled the young Ceres, protected from the freezing temperatures of space beneath a thin layer of ice. Across this ancient embryonic world, ice volcanoes broke through, transforming and renewing the surface as it was bombarded by the bodies that swarmed around it. Today we see just the lifeless remains of this geologically active world in the distinct mountainous landscape and sparkling salts that clothe it. But the subsurface ocean is long gone, locked away as a thick layer of ice between the surface and the core. This is a nascent planet that has been in deep stasis for billions of years. Frozen in time, it is a precious piece of history, an artifact that allows us to glimpse our origins and understand just how precarious a time this was for every planet, including our own. We now think that before Ceres could fulfill her potential, a great disturbance sent shock waves through what would eventually become the asteroid belt and cut its young life short. The vast amounts of rock and ice that made this part of the young solar system such a rich breeding ground for the birth of planets was wiped clean of almost all of its building material, leaving just a fraction of the material needed to build a planet, and nothing from which Ceres could grow. Computer simulations suggest that originally the asteroid belt contained enough material to build a planet the size of Earth, and perhaps that was once Ceres' destiny. Perhaps it was even destined to become a subterranean water world capable of supporting and nurturing life. But before any carbon chemistry could spark into seeds of life, Ceres' fate was sealed, triggered by the wanderings of a giant that lay beyond in the darkness. We now suspect that at this early time in the life of the solar system, as Jupiter circled the young sun, something caused the giant planet to change course and spiral inwards towards the sun, ploughing right through the asteroid belt. The resulting gravitational chaos scattered the contents of the asteroid belt far and wide. Embryonic planets were knocked out from their orbits. The building material of these planetesimals was thrown out and in towards the sun. Jupiter's charge displaced 99.9% of the material in this region of space, leaving Ceres half-formed, half-built, but with nothing more from which to grow. In this part of the solar system at least, the planetary construction business was shut down for good. How do we know such a dramatic turn in the solar system's history took place? The greatest evidence has come not from our own system, but from the study of other star systems and their planets, a field of science that has exploded in the last 30 years. Until the 20th century, the only evidence of how planetary systems formed and functioned came from one single source, Earth's solar system. Our own backyard was the one place that we had the technology to study, and that meant our view of how a planetary structure worked was deeply skewed towards the seemingly simple structure of a star at the center, 4 small rocky planets orbiting it, then a ring of millions of rocky pieces, remnants from its formation, followed by a series of 4 more planets, the gas giants. It has a pleasing, regular structure about it, all the rocky planets sitting close to the star and the gas giants orbiting further out. We supposed this must be the natural order of things, the way that solar systems have to form. But that all changed when the technology arrived to allow us to detect planets around distant stars. It soon became clear that our solar system is not typical at all. It may, in fact, be very odd indeed. In most of the planetary systems we've observed, the setup is remarkably different to our own. As we have extended our gaze and explored the structure around other stars with the help of exoplanet hunting technology like the extraordinary Kepler telescope, we've begun to see that one of the most commonplace categories of planet is completely missing from our own. Inward of Mercury, our solar system is essentially an empty void. But look at the equivalent region around most stars we have studied, and we often find it packed with a completely different class of planet, super-Earths. These worlds are between 2 and 8 times the mass of the Earth, with thick hydrogen-rich atmospheres. They sit incredibly close in to their stars, orbiting at a rate that makes the head spin. The first discovery of a super-Earth around a main sequence star like our own was made back in 2005 by a team led by Eugenio Riviera, using data from the Keck Observatory in Hawaii. Gliese 876d is an exoplanet almost 7 times the size of the Earth, which is orbiting just 3 million kilometers away from its red dwarf star, Gliese 876. Thought to be a rocky planet with surface temperatures estimated to approach 341 degrees Celsius, with an orbital period, year, of just under 2 days, this is a world completely inhospitable to life. To understand why this rocky planet is found so close in to the Sun, we need to understand the rest of the planetary system. And in the case of Gliese 876, that means looking at the 3 other planets circling further out from the star. The first of these planets to be discovered, and one of the earliest ever observations of an exoplanet, is 876b. Discovered in 1998 by the legendary planet hunter Jeff Marcy, we believe this world is a gas giant at least twice the size of Jupiter, but orbiting much closer to its parent star. In fact, at just 0.2 AU, 30 million kilometers, this massive planet is orbiting much closer in than Mercury orbits the Sun. At that distance, 876b zooms around on its orbit once every 61 days, compared with Jupiter's stately 12-year journey around the Sun. Either side of this giant planet are 2 other worlds, 876c, a gas giant 3/4 the size of Jupiter, and 876e, a planet we think is about the same size as Uranus. All 4 of these worlds orbit within a distance less than the orbit of Mercury. It's as if the whole planetary system has been squashed, packed in tightly around the star, and this configuration is far from rare. As we've explored more and more planetary systems, we've discovered this combination of super-Earths and close-orbiting gas giants is the nearest to a normal layout we observe.
I can do this.
I can do this. You can do this. I can do this. You can do this. I can do this.
There's luxury you can feel, and there's luxury that lets you feel infinitely you.
If you're antisocial like I am most of the time, but you're still curious or looking into solar power for your home and you don't want to talk to a salesperson either through Zoom or having them come out to your house, or you don't want to talk to anybody at all in order to get a ballpark instant estimate, then go ahead and click the button right here on this video, and that's going to take you to our new solar calculator that's combined not only with our data here at Solar Energy World, but it's also combined with Google's Project Sunroof data to give us radiance projections based off of your local area, and that's going to tell us how much you're going to be able to produce on a yearly basis as far as your kilowatt hour production. So if you didn't already know, it doesn't cost you anything up front at all to switch to solar power. You can literally pay $0 up front, get the solar system installed on your roof or somewhere on your property, and you can actually start saving money from month 1. Again, once you click that button, just provide a few pieces of information and you're going to get an instant ballpark solar estimate. That way you can at least get an idea. And at that point, you can move forward with a finalized solar estimate from our company here at Solar Energy World. And at that point, you're probably going to have to talk to somebody, but don't worry, we are very nice people and we walk you through every step of the way. Go ahead and click the button on this video to get a free instant ballpark estimate from our company here at Solar Energy World, and hopefully we'll be talking to you soon.
What underlies this is the fact that planetary systems are not the static and stable systems we had always assumed them to be. Far from the heavens being full of planets following eternal clockwork rhythms, most systems, including our own, are chaotic, dynamic, and turbulent. The reason for this is that, particularly early on in the infancy of a new system, planets frequently migrate, forming in one part of the system before wandering off into different zones. There are a number of different mechanisms behind these wanderings, but perhaps the most formative on the evolution of a planetary system is the Type II migration that occurs to gas giants early on in their lives. A gas giant planet like Gliese 876c would almost certainly have begun its life far further out than it is today, in a region more akin to where we see Jupiter or Saturn in our own solar system. At the very earliest stages of its existence, as this newly formed planet orbited within the cloud of gas and dust of its formation, the planet began to clear a path in its wake, and in doing so triggered a process that would transform its orbit. A shift in its gravitational interactions with the gas-rich disk would have slightly reduced its angular momentum and sent the planet on a different course, spiraling inwards towards the star at the center of the system. This seems to be a common path trodden by many gas giants around distant stars, and is the reason we find a preponderance of so-called hot Jupiters, massive gas giants sitting so close to a star that they orbit it in less than 10 days. The effects of these migrations have an impact far greater than just this, though. In ploughing inwards, a migrating gas giant like Gliese 876c ends up clearing vast areas of space, halting any planetary formation, and instead pushing material inwards towards the star, creating the perfect scenario for super-Earths like 876d to form. This cosmic pinball is the reason why so many of the planetary systems we've been able to explore follow the pattern of hot-ish Jupiter and super-Earths. But why not ours? What was different about the history of our solar system that led to the more expansive layout we see today? Scientists suspect the answer lies with our own gas giant, Jupiter, and the journey it took across the young solar system. The story of Jupiter begins not in the far reaches of the solar system, 778 million kilometers from the Sun, where it orbits today, but much closer in. We now think that almost 5 billion years ago, Jupiter formed around 520 million kilometers, 3.5 AU, from the Sun. At this time, the young giant was still surrounded by the disk of gas and dust from which it had arisen. But Jupiter began to slowly but surely clear its path through the cloud and debris. Over a relatively short period of time of just a few million years, the path through its orbit became completely clear, and just like the huge gas giants we've observed around alien stars like Gliese 876, this caused Jupiter to start spiraling inwards towards the Sun. This process was driven by the gravitational interaction between Jupiter and the cloud of gas, which, as it fell into the Sun itself, effectively dragged the planet with it. This was no subtle shift in Jupiter's orbit. While it spiraled inwards, it would keep falling closer and closer to the Sun, passing through the region of asteroid belt and robbing planetary hopefuls like Ceres and Vesta of the material they needed to complete the journey to planethood. But this was just the start of Jupiter's reign of terror. Further and further the young Jupiter fell, until it reached the vicinity of where Mars orbits today, just 225 million kilometers or so from the Sun. This was no quiet visitor to our local neighborhood. A planet of this size can wreak havoc just by its proximity, and Jupiter's arrival in the inner solar system did just that, transforming the destiny of many of the emerging new worlds, including our own. Lee Fletcher from Jupiter Icy Moons Explorer mission explains this action as a tug-of-war. Between the orbits of Mars and Jupiter, we have a large accumulation of objects, rocky objects mostly, known as the asteroid belt. They're not able to form and agglomerate into a complete planet because of the constant tug-of-war between the gravitational forces of the Sun and of Jupiter. So what we see today is a large disk of objects that could be the remnants left over from the formation of our solar system. To understand just how powerful a presence Jupiter must have been as it marauded around the inner solar system, we need to look no further than the worlds it has in its iron grip today. Jupiter has, at the time of...
I'm the team mascot, and boy am I running late. Ow, what a hit. And if you have cut-rate car insurance, the cost to cover that might tank your season. So get Allstate and be better protected from mayhem, like me.
Writing 79 known moons held in its orbit by the powerful gravitational field that is generated by the planet's enormous mass, a powerful force field that reaches out from the planet deep into the solar system. It's what has made Jupiter so destructive in the past, and through our exploration of the Jovian system, we have also witnessed its awesome power today. Nowhere is this power more dramatically revealed than on Io, the closest of all the moons to Jupiter. Io orbits just 350,000 kilometers from the cloud tops of its mother planet, a distance that makes it a gravitationally tortured world. A volcanic vision of hell, this is the most geologically active object in the solar system, with over 400 active volcanoes, from which lava flows stretch hundreds of kilometers across the moon's surface, and vast clouds of pyroclastic material blow hundreds of kilometers up into space, creating distinctive umbrella-shaped plumes above its surface. The surface of Io is perhaps the closest that our solar system has to offer of a vision of hell, and all of this activity is created not by ancient internal heat as we see on our planet Earth, but by the power and the influence of Jupiter's gravitational pull. Here on Earth, the volcanism that we see across our planet is driven by a combination of the heat that remains from our planet's violent formation and that which is released from the decay of radioactive elements locked away in the planet's interior. This heat, combined with the high pressures below the surface, creates the molten rock that pools within the mantle layer of the Earth, and then in certain places this magma finds a route to the surface, creating a volcano. On Io, the volcanism is nothing like this. Instead, it's being generated by a completely different mechanism, a process called tidal heating, that is driven in large part by its proximity to Jupiter and the gravitational tug-of-war between other nearby moons. Io is caught between the vast mass of Jupiter on one side and the three other Galilean moons, Europa, Ganymede, and Callisto, on the other, a dynamic that pulls in different directions to violent effect. It's a dynamic that we see in part on our planet every day, as the force of gravity flexes its muscles in the interaction between the Earth and the Moon, creating the twice-daily ebb and flow of our tides. On Earth, the gravitational tug of the Moon creates a tidal force that moves vast volumes of water around the planet, with the biggest difference between low and high tide creating a shift of a maximum of 12 meters in the height of water. The same principle also applies on the surface of the Moon, where the gravitational pull of the Earth creates tides not of water, but of rock. Moon tides are small changes in the height of rocks on the lunar surface caused by the pull of the Earth's gravity. In the case of the Earth-Moon system, these rock tides are measured in just a few centimeters, but Io tells a very different story. Io is roughly the same distance from Jupiter as our Moon is from Earth, and both moons are of equal size. But because Jupiter is so much more massive, the tidal forces it generates are much greater, with the gravitational pull of Jupiter moving the bulge of rock tides up to 100 meters between low and high tide. That's 5 times the height of any tide here on Earth, lifting the levels of solid rock up and down. In fact, Io contains the least amount of water of any known object in the solar system. But this is not the end of Io's torture. Its relationship with the other large moons, particularly the next moon out, Europa, also adds to the destructive forces that are pulling the very substance of Io apart. Io whips around Jupiter much quicker than our moon goes around the Earth, once again due to the mass of Jupiter, completing an orbit once every 42 hours. If left alone, Io would complete this orbit in a near-perfect circle around the giant planet. But Io is far from alone, and with Europa circling Jupiter precisely once every 2 orbits of Io, it means that in every second orbit, Europa and Io line up, and that rhythmic orbit has consequences. This is what's known as an orbital resonance, and the result is that it gives Io an additional gravitational kick that moves the moon's orbit out of a circle and into an ellipse. Ganymede is also in a resonant orbit with Io in a 1:4 orbital period ratio, and the outcome of this is that as Io orbits, the gravitational forces are constantly shifting and changing, and that stretches and squashes the moon, creating vast amounts of friction that causes its interior to heat up. It's a process called tidal heating, and it's this generation of heat that produces Io's volcanoes, raising the temperature in its interior to over 1,200 degrees Celsius, and creating the violent world of lava lakes and volcanic plumes that we've witnessed through the eyes of Galileo and Voyager. The pull of the 2 moons on Io also stops it gradually falling inwards to Jupiter and being completely ripped apart. Io is an extraordinary example of the power of Jupiter, and a demonstration of how this planet can shape and change the destiny of worlds. Because of its huge mass and the intense gravitational force this produces, any planet or moon that gets too close to it is under threat. While Earth is at a relatively safe distance today, 4.5 billion years ago, as Jupiter moved into the inner solar system, it began to exert its power right in the spot where Mars and our own world were beginning to form. 4.5 billion years ago, the region of the solar system we call home was densely packed with gas and rock, a planetary nursery full of embryonic worlds, each with a different destiny in store. But this fertile space was about to be thrown into chaos by the solar system's most unwelcome of visitors. As Jupiter was pulled from its distant orbit and continued its inwards descent, it paused in this planetary breeding ground. The consequences of this action would be significant and far-reaching. Detailed simulations of the impact this wandering Jupiter would have made suggest that the fate of any super-Earths caught in mid-formation would have been thrown into chaos. The models suggest that Jupiter's inward journey would have driven thousands upon thousands of planetesimals, many over 100 kilometers wide, spiraling into the inner solar system. This planetary breeding ground was turned into a battleground, as Jupiter's presence threw the orbits of any newly forming super-Earths into the overlapping paths of thousands of massive blocks of rock and ice. The result was carnage, a cascade of collisions that blew apart planets and left a trail of fragmentary worlds in its wake, a chain reaction that would culminate in the formation of a spiraling swirl of gas, dust, and rock that would have swept any surviving super-Earths towards the sun and ultimately to their destruction. In what was just a fleeting moment in the history of our solar system, its destiny changed forever. Our planet would not fit the norm of super-Earths and the tightly packed gas giants that we see across the Milky Way. Instead, we think the inner solar system would have been swept clear of up to 90% of the rocky material thrown in by Jupiter. With just crumbs remaining, 4 small terrestrial planets began to form from the rubble. With Jupiter marauding in its orbit, much of the material that could have gone on to form Mars was lost, leaving the planet with enough scraps to make a planet half its potential size, and transforming it from a possible habitat for life to a world that would freeze and die in its adolescence. Just that little bit further in, Earth found itself forming in a slightly more substantial ring of gas and dust that would make it the largest of all the terrestrial.
I can do this.
luxury that lets you feel infinitely you.
Terrestrial planets. A lucky escape for our future home, because had Jupiter continued on its inward path, Earth might never have formed at all. But just as it looked like it would sweep everything away, Jupiter stopped in its tracks. On its inward journey, Jupiter had transformed the inner solar system, sweeping away the formative giant planets and leaving just enough material for Mars, Earth, Venus, and Mercury to form. But the stage was now set for another player to enter the story and shift the destiny of both our world and the solar system once again. Waiting in the shadows of the outer solar system, another massive planet was lurking that we now think pulled Jupiter back from the brink. Saturn, a gas giant not as big as Jupiter but enormous nonetheless, began its own slow drift inwards towards the Sun. Formed much further out than Jupiter, as Saturn began turning inwards, it would have a profound effect on Jupiter's trajectory. As the two giants drew closer together, they became locked in an intimate gravitational dance, an orbital resonance that meant that for every orbit Saturn made around the Sun, Jupiter made 2 circuits, exerting a regular periodic gravitational influence on each other as the two giant worlds passed close by. The result of this orbital resonance between Jupiter and Saturn cleared out all of the gas and dust between the two planets, creating a gap in the disk of the early solar system. And this interaction between the two resonant planets and the gas and dust at the edge of the gap resulted in both planets changing tack. The orbits of both Saturn and Jupiter began to move outwards, away from the Sun, preventing Jupiter from moving any further into the inner solar system. Earth was given a reprieve, and Jupiter was dragged back out into the asteroid belt once more. This change in direction has become known as the Grand Tack Hypothesis, a nod to the action of a sailboat as it tacks and changes course while it travels against the direction of the wind. Just like a sailboat, the theory suggests Jupiter tacked around 1.5 AU from the Sun, in the current orbit of Mars, changing direction and pulling back out to its current orbit at 5.2 AU. It's a theory that's been driven by using advanced computer modeling, which helps to explain many of the inconsistencies between our solar system and the hundreds of other planetary systems we've recently observed. It's the Grand Tack that accounts for the lack of super-Earths and explains the presence of only a handful of small rocky worlds with thinner atmospheres than those observed around other stars. The Grand Tack also allows us to explain the unusually small size of Mars, which simulations predict should be at least half the mass of the Earth, if not bigger, rather than the 0.107 Earth's mass we find it to be. It also helps explain the odd inhabitants of the asteroid belt, transformed by Jupiter's journey not just once but twice across this region of space. This is why we see half-finished planets like Ceres and Vesta left starved of building material, and an asteroid belt that has a surprisingly small mass, with objects that appear to originate from both inside and outside Jupiter's orbit, and have a wide range of eccentric orbits themselves. Jupiter, the father of the skies and ruler of the heavens, had spread its hand far and wide, sculpting the precious solar system we see today in the space of just a few million years. Before coming to rest, though, it would grant one more precious gift to the newly forming planet Earth. As Jupiter was dragged out, crossing the asteroid belt for a second time, it encountered a region full of objects rich in water and bearing minerals, and Jupiter's trajectory caused these objects to be flung back into the inner solar system. They crashed into the young planets and moons with an intensity never seen before or since, in a period known as the Late Heavy Bombardment. It transformed the makeup of the inner solar system, delivering a large percentage of the water Earth holds on its surface today. It's extraordinary to think that it was Jupiter that was responsible for the delivery of the most important ingredient of life, the water that provided an ideal environment for life to spark and thrive in one unbroken line for the last 4 billion years. This story offers an extraordinary understanding of the power Jupiter has wielded over all of our lives. The more we learn about the formation of solar systems, and the more we try to model a system like ours with 4 terrestrial, water-rich planets close to the star and the gas giants further out, the more we learn that perhaps all these things had to happen. These unlikely movements and interactions between the planets were necessary to produce a system like ours, and a planet like ours. So if events like the tack of Jupiter are, as we believe them to be, extremely uncommon, the conditions for the formation of Earth-like planets, terrestrial worlds with plenty of liquid water beneath the gentle pressures of a thin blue line, must be exceedingly uncommon. It's a humbling thought to begin to comprehend that the Earth may not just be a rare rock in our solar system, but a rock that only exists because of the rare system of planets within which it evolved. All the evidence is beginning to suggest that we may be living on a tiny oasis within a vast desert, devoid of life and stretching out across the...
Full Sail University is where you can get hands-on experience with emerging technologies. Whether you're on campus or online, we offer degrees in user experience, information technology, and cybersecurity. Learn how to create pathways for information with cloud technologies and protect against cyber threats, so you can go on to develop the future of computing and how we interact with the world.
My son is Braxton, and he was diagnosed with a brain tumor. And they said it's an extremely rare cancer. Braxton went in for an 8-hour surgery. We kissed him goodbye. You're scared, because you don't know what he'll be like after. And everybody was saying, what about St. Jude? What about St. Jude? And with all my reading about success rates, you know that he has the best chance here. We're looking at 3 to 8 months of chemo. The hope is that Braxton gets to go home. In a couple years, our plan is T-ball. So you just gotta keep thinking of T-ball, but it's hard.
You can join the battle to save lives by becoming a partner in Hope for only $19 a month. We'll send you this St. Jude t-shirt you can wear to show your support for the children of St. Jude.
Braxton was 6 weeks old.
Milky Way. Today, Jupiter has settled into a regular orbit at the far side of the asteroid belt, its days of marauding through the solar system at an end. Established in a stable orbit for almost 4 billion years, it has looked down on our planet as a distant light in the sky, unchanging while the work of evolution by natural selection has transformed the first sparks of life on Earth into the endless, beautiful forms that we witness today. But although distant and seemingly detached, Jupiter's influence has been far from benign. The history of life on Earth has been interrupted by numerous cataclysms, impacts with asteroids that have fundamentally shifted life again and again. And the hand behind these disruptions? It's Jupiter, that has continued to hold immense sway over our planet, exerting its influence on the asteroid belt with just the smallest of nudges, the difference between existence and extinction. At 16:53 UTC on the 18th of October 1989, the Space Shuttle Atlantis took off from the Kennedy Space Center in Florida, carrying the Galileo spacecraft carefully packed away in its hold. Released into Earth's orbit from the cargo bay just a few hours later, the probe would begin a 6-year journey to Jupiter that would utilize flybys of Earth and Venus to propel it on its 4.6 million kilometer voyage across the solar system. Entering orbit around the giant planet on the 8th of December 1995, Galileo would not only become the first spacecraft to orbit Jupiter, but also the first craft to orbit any of the outer planets. It spent nearly 8 years in the Jovian system and explored the giant planet and its menagerie of moons in intricate detail for the very first time, revealing a host of new discoveries. From precise measurements of Jupiter's atmosphere and observation of its giant thunderstorms, to discovering liquid water under the surface of the moon Europa and the first detailed studies of the intense volcanic activity of Io, this was a mission that opened our eyes to the beauty and diversity of the Jovian system, in a level of detail that we could scarcely have imagined possible. But long before Galileo even arrived, this 2-ton explorer would already have changed our view of the solar system. Entering the asteroid belt in August 1991, Galileo performed the first close-up flyby of an asteroid, passing within 1,500 kilometers of 951 Gaspra, and returning the first detailed images of this rocky remnant back to Earth. Its next close encounter would come almost 2 years later, when flying past 243 Ida, the probe discovered that this asteroid had its own moon,